So let's begin. And here's the question that the presentation is centered around. Do habitable worlds require magnetic fields? And as a bit of an anecdote, I'll say that when I became a university professor, which is not anything that I ever intended or really wanted to do, but now it's something that I love, I felt like my own science, in addition to continuing my own science, I needed to be thinking big thoughts. And I don't know if that's accurate or not, that that's what you need to do as a professor, but when I was starting out, I was very intimidated by this job and thought I need to be thinking about science with a capital S. What is the science question that I would love to center my career around for the next 10 years? And so this is the question that I came up with, something that really interests me, that I think is of fundamental importance, not just to my small community, but maybe a larger space science community. And it's something that I think that we can address within the span of my career and make good progress on. Okay, so that's the question. Do habitable worlds require magnetic fields? And on the slide here, you can see 3 terrestrial planets, Venus, Earth, and Mars. Those are the 3 rocky worlds in our solar system that have substantial atmospheres. Mercury and the Moon are also rocky worlds, but they don't have very substantial atmospheres at all. And so really, why is Earth habitable but Venus and Mars not? And does the fact that Earth has a magnetic field play into the answer to that question of why Earth is habitable? So I'll advance one slide here and say that that question that I posed at the top is a really hard question. I didn't realize quite what I was getting myself into. So I prefer to start with 2 easier questions. One, do magnetic fields affect planets? Not whether they're habitable, but do they affect the world at all? And so here are 2 examples that suggest that the answer is yes. On the left is Jupiter's moon Ganymede. It's the largest moon in the solar system. It's larger than Mercury, it's larger than our moon, it's larger than Pluto, a dwarf planet. So it's a large icy world orbiting Jupiter. And if you could see this image, or if you can see this image, you notice that the middle latitudes, the regions clustered near the equator, are darker, they're more brown than the things near the poles of Ganymede. And the poles are whiter and grayer. And that's not because Ganymede has polar caps, the whole world is ice. The reason that it's darker in the center of Ganymede is because Ganymede has a magnetic field. And if you could close your eyes and draw magnetic field lines coming from this world, it would look a lot like Earth, with field lines coming out from the interior, coming out maybe near the North Pole, but not exactly at it, and looping around and re-intersecting the surface somewhere in the southern hemisphere. And it turns out the dark regions here are the regions that are protected by magnetic fields. And so they deflect charged particles that are near Jupiter and prevent them from ever reaching the surface of the moon. The northern and southern caps of Ganymede are not protected. There, the magnetic field lines from Ganymede come out from the interior and they connect to Jupiter's magnetic field, and they connect all the way up to Jupiter's atmosphere. And so any really energetic particles that are on those magnetic field lines go crashing into Ganymede at the top or the bottom, and they lead to space weathering, and it looks much brighter and whiter at the top and the bottom. Similarly, on this slide on the right is a small region of the moon called Reiner Gamma. Reiner Gamma is a place that's a great example of something that's called an albedo swirl on the moon, basically a brightness variation. And you can see milky white regions of the surface and dark black lanes, and lots of structure here and how bright the surface is to even visible cameras at the moon. And those, it turns out, Reiner Gamma and other regions like this on the moon are all places where there is a region of the crust of the moon that is magnetized. Just like there are magnetic regions of the crust here on Earth and magnetic rocks, this is a region that's maybe 10 or 30 kilometers across on the moon where there's magnetic minerals underneath the surface. And so the idea is that this small-scale magnetic field on the moon protects the surface and somehow leads to variations in the brightness. And scientists are still trying to figure out whether charged particles from the solar wind are not impacting the moon in these locations, or dust on the surface of the moon becomes charged and hops around and organizes itself into white and dark lanes. But regardless, the answer to the question is yes, magnetic fields do affect planets. Got it. Okay, I'm just checking the chats periodically. Okay, the next easy question is, do magnetic fields affect atmospheres? And I don't need to spend a very long time on this slide because aurora on Earth are obvious and incredibly visual and incredibly beautiful examples of the fact that the answer to this question is yes. Charged particles in Earth's magnetic field that are trapped there, that likely came originally from the stream of particles from the sun, the solar wind, come crashing into Earth's atmosphere where magnetic field lines intersect the atmosphere. They excite atoms and molecules that are already in Earth's atmosphere when they come crashing in. Those excited atoms and molecules, when they relax again, when they give away their energy, they glow. And that's why we see aurora. And so essentially you can see structure in Earth's magnetic field by looking at and studying aurora.
So we have our first question, Dave, and that is whether large areas like the one on the moon have a north-south orientation. Is it like a large buried bar magnet, or is it more diffuse?
So yeah, there is polarity to those magnetic fields. You can measure basically the equivalent of what a bar magnet would give you if you buried a bar magnet under the lunar crust. And different regions of the moon have different orientations of that magnetic material. So some are oriented vertically, some are oriented horizontally, some are oriented north-south, others oriented east-west. And where some regions of these moons are close to each other, those separate bar magnets interact with each other and create a more complex magnetic field. But I will say that the magnetic fields on the moon are very weak compared both to the magnetic fields on Mars and Earth's magnetic field. So they're probably the weakest, they're probably some of the weakest planetary magnetic fields that we've studied anywhere in the solar system. But they still affect the moon.
Thanks.
Sure. Okay, so let's come back to the guiding question that I said was harder. Do habitable planets require magnetic fields? If you're going to have life on a world, does that world need to have a magnetic field? So the answer, in some sense, is incredibly easy. For those of you who can see the figure, there's Venus, Earth, and Mars again from the cover slide, and only Earth has a big magnetic field. And empirically, the answer is yes, habitable planets require magnetic fields. Earth is the only inhabited planet that we know about, and it's the only terrestrial planet with an atmosphere that has a magnetic field. Earth is habitable. Mars, it's easy to argue, is not habitable at the surface. Venus is not habitable at the surface either. So empirically, we're done. And this was the shortest MAVEN Outreach webinar ever. However, that's working with a small number of worlds, and small statistics are always dangerous to work with, especially if you're doing things empirically without little attempt at understanding. So we're going to spend the rest of our time exploring this question a little more. Great. So this is something very simple. It's something that I'm sure is incredibly accessible to all of you, but I put it in here because it's something that I show to undergraduates who are non-astronomers to make the point that life doesn't need very much. Of the 6 million or so different species of life on Earth, we know that the 3 things that every species needs are these 3. For those of you who can't see the slide, it's pretty easy. On the left, all life needs an energy source. So for those of us on this webinar, that energy source is ultimately the sun, because the food that we eat got its energy from the sun, whether it be animal or plant, because animals ate plants, and that plant got its energy from the sun. But there's life on Earth that thrives on energy that's derived from chemical reactions, for example. So there needs to be an energy source. And this is not that difficult on the worlds that we know about in the solar system. There's available energy on every single body in the solar system, whether it be from the sun or the interior of the planet or something else. So this is not a showstopper. On the right, all life needs food in some form. And this is a very literal interpretation of food with peppers and bananas and carrots. But really, when you break down those peppers and bananas and carrots, what all life needs are just 6 chemical elements: CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur in some combination. And it turns out carbon is readily available on every world in the solar system that we know about. H and N and O and S, and even phosphorus you can find many or most places in the solar system. So the chemical elements that we need to thrive are also available everywhere in some combination. Really, the hard thing to get is water. And it's sort of surprising to think that all 6 million species on Earth need water in liquid form, but it's true. Even life in Antarctic dry valleys, where it doesn't rain more than once a decade or more than that, that life metabolizes incredibly slowly, and it grows and thrives on available liquid water when it becomes available. Life deep underground needs liquid water. You and I need liquid water. Water in solid form isn't going to do. We can't thrive on ice. We need liquid. Water in gaseous form is not going to do. Water vapor doesn't help us that much. It feels pleasant, but we need water as liquid. We need the liquid droplets in that water vapor. Okay, so that's what we need. How do magnetic fields relate to these 3 things? Well, let's throw away food. Let's throw away energy, since liquid water is the hard thing. And let's think about how magnetic fields relate to that. And that's the motivation for the rest of our time together. So I just made the point that all life requires liquid water. Great. And I'm going to limit our discussion to the surfaces of other worlds. And we could spend a long time talking about Jupiter's moon Europa, or Saturn's moon Enceladus, or other subsurface oceans in the solar system, or even the subsurface of Mars as well. And I would love to talk about those. But if we're going to detect life on another world, there are significant challenges posed by trying to look underneath the surface of a planet, especially when we started talking about worlds orbiting other stars. And so for now, I'm going to intentionally limit our discussion to looking for evidence of life, or life that could thrive at the surface of a planet. And if that's true, we need liquid water at the surface of a planet. And if we were to put liquid water on the moon, it wouldn't stay there. It would all sublime away, basically. It would boil away. And water couldn't exist as liquid. What you need is an atmosphere providing enough pressure on the surface for water to be happy as a liquid. So you have to have some kind of atmosphere on the world, which is why we limit ourselves to talking about Venus, Earth, and Mars for terrestrial planets. And it's been assumed since the 1980s that a planet's magnetic field plays some role in preventing an atmosphere from being stripped away or escaping away to space. You often hear this analogy of Earth's magnetic field being a shield for the atmosphere. What's it shielding the atmosphere from? It's shielding the atmosphere from charged particles coming from the sun, the solar wind. So those are protons and electrons at 400 kilometers per second, somewhere between 200 and 700 kilometers per second, that are screaming towards the atmosphere, and Earth's magnetic field provides some shield. So this has been canonical wisdom since the 1980s, but in the past 10 years, there's been some reason to question this assumption and to evaluate it critically. Maybe this assumption that you need a magnetic field to retain an atmosphere is wrong. And as an example, Venus has 90 times Earth's atmosphere, but doesn't have a magnetic field. However, Venus isn't a place that's a great example because it's not habitable at the surface. There's so much greenhouse effect there. And that's in part because hydrogen has been stripped away to space. And if Venus had a magnetic field, maybe the hydrogen would not have been stripped away to space. So there's reason to start thinking about this assumption. And one more disclaimer, I know that radiation can be very harmful for life, and for single-celled life, radiation can destroy it entirely, and magnetic fields can shield the surface of a planet from radiation. I'm not going to talk about that here today, and magnetic fields can be very important for that. Instead, I'm going to focus on retaining an atmosphere.
We have a question. Is cosmic ray flux important at all compared to the stellar wind flux for atmospheric stripping?
In our stellar system, no. The stellar wind flux is orders of magnitude larger than the cosmic ray flux, both in terms of number and in terms of energy per time that's encountering the atmosphere. It is important for the radiation question that I said I'm going to ignore for the rest of the talk. So there, cosmic ray flux, those cosmic rays carry so much energy per cosmic ray that they can be really damaging to life compared to, say, a regular old stellar wind particle. But it might be true that in other systems, the stellar wind flux is so low that cosmic ray flux becomes important there.
Thank you.
Sure. Okay, so now we're going to do some simple physics. And I'm going to argue that magnetic fields really should protect atmospheres, that this idea from 30 years ago is correct. The reason I'm going to argue that is because the physics are so simple. Really, I kind of already described them. A magnetized planet deflects the solar wind, the stellar wind, charged particles far from the atmosphere. So they can never really access the atmosphere other than being processed in the magnetic field and resulting in aurora or something like that. So the stellar wind can't hit the atmosphere. That means there's less energy for the top of the atmosphere. And if you're depositing less energy in the atmosphere, then that's less energy that can be used to give particles enough oomph to escape the atmosphere, to escape the gravitational well. So it's really a simple idea. Atmosphere can't escape very efficiently. And there's some qualitative support for this idea. One that I'm not going to show you in the slides an example of, I'll just talk about, is this. There are chemical signatures in the atmospheres of Venus and Mars that suggest that they lost more atmosphere than Earth did. And so I'll use jargony words, but not go into it too much. If you look at isotopes of different chemicals, for example, deuterium and hydrogen are basically the same kind of molecule, but one is heavier than the other, but they behave chemically in the same way. When we look at Venus and Mars, we see that their atmospheres are enriched in heavy isotopes. And heavy isotopes are harder to pull out of an atmosphere. The planet holds on to them more easily. And so when we look at Venus and Mars, we infer that the light isotope has been pulled away to space, leaving the heavy one behind. And we don't see this nearly as much in Earth's atmosphere. And Earth has a magnetic field. That suggests that the unmagnetized planets have lost important stuff over time that Earth hasn't. And the reason I'm not showing you qualitative evidence for that is because, not to impugn anyone, they're all my friends, but some of those plots are just not that much more informative than me saying that out loud. Instead, I'll give this other piece of evidence that a study several years ago demonstrated that Earth and Mars may respond differently to the same solar storm. So for those of you who can see the slides, there's kind of a cartoon animation, a NASA-style animation, showing a solar storm from the sun that swept by Earth and Mars when Earth and Mars were lined up with respect to the sun. And we had spacecraft at both planets that were measuring the response of the atmosphere and how many particles escaped from the atmosphere, and the planets responded differently. So I can show you that as well in the slides, but if you can't see the slides, it's not a big deal. There are two panels here, one on the top, one on the bottom. The one on the top is for Earth, and it shows how much escape there was from Earth's atmosphere as a function of time. And in black, you see how much escape there was as a function of time before the solar storm hit. And in orange, right on top, you see how much escape there was as a function of time during the solar storm. And escape increased by a factor of 2 or 3 or something like that during the solar storm at Earth. So escape was influenced by solar storms. But now if you look at the bottom, for those of you who can see it, in black, from this orbiting Mars spacecraft from the European Space Agency that got very far from Mars. So we don't have continuous data, but once per orbit, the escape was measured from Mars. And both before and after the solar storm, escape rates were pretty low. And during the solar storm, there was a big spike in escape rates by an order of magnitude or more. And by escape, I mean number of particles per second. In this case, it's the number of oxygen ions being lost every second. But in the Earth diagram, I intentionally blocked out the numbers and the units. You can see the hash marks, the big hash marks are factors of 10. So Mars responded in a big way to the solar storm. Earth responded in a small way to the solar storm. That suggests maybe that the lack of magnetic field at Mars led to more escape. Okay, so I've just argued that what we thought 30 years ago or 40 years ago is correct. On the next slide, I'm going to argue that it's incorrect. I'm going to argue that magnetic fields should not protect an atmosphere. And the reason I'm going to argue that is because it's really simple physics, just like the other slide, but in a different way. And the analogy here for me that I'm starting to settle on is the sails on a ship. You don't have sails on a ship because sails are pretty things to put on a ship. You have sails on a ship because they collect more energy from the wind than the ship would on its own. And that's why you put them up. And a magnetic field for a planet is effectively a large energy collector from the solar wind. So a magnetized planet is going to encounter more energy from the solar wind than an unmagnetized planet. If we could turn off Earth's magnetic field right now, Earth's magnetic field would collect less energy from the solar wind. So it's a larger cross-section for that planet. That energy that's collected by the magnetic field ultimately gets transferred to the atmosphere along the magnetic field lines using fancy plasma physics-y stuff that I only barely understand. But the visual reminder of that is aurora. That's a great sign that energy is transferred along magnetic field lines to the atmosphere. So we know it's happening. And that energy, once it gets put into the atmosphere at the North and South Pole, can lead to escape of particles. And we've measured escaping oxygen from Earth's atmosphere in the North Polar Cap and the South Polar Cap. And that escape, even though it's not global like it is at Mars, it's really efficient in those places. A lot of particles are being pulled out. So that's the simple physics that suggests maybe magnetic fields don't protect atmospheres as much as we thought. Maybe they, in fact, lead to more escape of the atmosphere than if the planet didn't have a magnetic field. That's a hard idea to test, but there's qualitative support for those ideas. So one thing that I'm not showing on the slide, I'll just say, is that spacecraft at all 3 planets have measured escaping charged particles. And there are large uncertainties on those measurements, an order of magnitude uncertainty on each of the measurements. But to within error, Venus, Earth, and Mars are all losing roughly the same amount of charged particles every second right now. And Earth is magnetized, and Venus and Mars are not. Another thing that I am showing in this diagram, again, where I've boxed out the units, is a correlation between how much energy is striking Earth's atmosphere from the solar wind. We can measure that with spacecraft. And how many particles are observed escaping out of Earth's polar cusps of the magnetic field, the places where aurora happened. And if you can see the diagram, you see that, okay, there are orders of magnitude on this diagram, and there's a lot of scatter, but it's pretty much proportional. The more energy you put in, the more particles you get that are squeezed out of the atmosphere as a result. So the magnetic field isn't really shielding the atmosphere incredibly effectively. If the solar wind blows harder, more escape happens. Maybe the magnetic field is limiting it a little bit, but it's not completely blocking it.
Okay, we've got a question, but don't magnetic fields deflect a lot of the solar wind rather than absorbing it?
Yeah, this is a great question. How can you have it both ways? And the answer is yes, they do. And I could throw a tennis ball at you, and it could deflect off of you, not be absorbed by you, but still give you energy. And so what's happening is these solar wind, these charged particles, as they encounter the magnetic field, they're giving some momentum to the magnetic field, some energy flux to the magnetic field as they're deflected. And that momentum and energy flux is what's used by the magnetic field and transferred down to the atmosphere, even though the particle itself was deflected. Okay, so hopefully I've outlined a question. It's a question that's really interesting to me, and I really like the idea that simple physics lends support to each of the two sides. So how do we resolve this issue? So with the remaining time, I'll tell you a little bit about the efforts we're making to figure it out. Okay, so first, my question at the top of the talk was, do habitable worlds require magnetic fields? That sounds like a well-defined question, but when I sat down to really think about how to answer it, I realized that for me, it was actually not that well constrained. It was a poorly defined question. So I instead rewrote the question 3 different times, getting more strict each time I wrote it. So that's what you can see on the slide if you have the slides. The first question, the easiest one, the least strict one, is all other things being equal. Does a planet with a magnetic field lose less atmosphere than a planet without? So that's the same thing as asking, if we were to suddenly turn off Earth's magnetic field, would atmospheric escape increase? Okay, that's a question that we should try to answer if we want to understand the answer to the main question. If we get more strict, we can say, all right, if so, is the reduction in escape when you add a magnetic field, is the change substantial enough to account for a difference in habitability at the surface on some time scale? So if we were to suddenly turn off Earth's magnetic field and escape were to increase, but it were to increase by 10 out of 10 to the 25th particles per second, who cares? Is the reduction substantial though? That's an important question too. And then the third and the most strict question in my mind is this: is it highly likely, or is it even required, that a planet that retains a habitable atmosphere have a magnetic field? Do you need to have a magnetic field to be habitable? When we're looking at planets around other stars, do we need to be checking to make sure those planets have magnetic fields or not? Does it really matter? So how can we bring data and models to bear on these questions? So let's talk about that for a little bit. But I will pause for just a second to see if there are any questions now that I've sort of set up the problem.
Folks, if you've got a question, please type it in the chat box, or if you don't have access to the chat box, please go ahead and unmute your line to ask a question.
And it's also a chance for me to get a drink of water. Okay, great. I'll do that once or twice more, hopefully, in our time here, just to make sure that it's not me droning on all the time. Okay, so now is where we're going to get more technical, and hopefully that's appreciated. So one way that you could go about answering this question are using global plasma models. So what do I mean by that? Global means we're going to simulate all of Venus, or all of Earth, or all of Mars, and how they interact with their environment. Plasma just means charged particles, and that's because the solar wind interacting with the atmospheres and the magnetic fields is thought to be important for driving atmospheric escape. And then models, it's a simulation, it's a whole world in a box in a computer where you have defined the physics equations that must be followed, the laws of physics that the world and the universe adhere to, and then you set some starting conditions, and then you've just let it go. So using these global models, you might imagine that it's easy to test this first question, all other things being equal. The planets with magnetic fields lose less atmosphere than planets without. And some people have started to do that, but not so much for atmospheric escape. So here's an example from 2008, a full decade ago, and this is the first one that I'm aware of, where someone who does computer simulations turned off the magnetic field and turned it on. But all they were looking for in this simulation, and this is a colleague of mine from Finland, Esa Kallio, all he did in his model was turn the magnetic field on and off, and he didn't turn on a very strong magnetic field. This is probably still 2 to 3 orders of magnitude, 1,000 times weaker than Earth's magnetic field strength. And that's because in these global models, it's really hard to be able to devise a computer model that's capable of doing both an unmagnetized world and a magnetized world. The best he could do was a really weak and puny magnetic field. But still, when he did that, you can see how different the magnetic field of the planet or the magnetic field around the planet looks. In the unmagnetized planet, the solar wind is carrying a magnetic field, sort of like spaghetti noodles, and those spaghetti noodles get draped around the conducting atmosphere of the planet. And they get hung up there, and then they slip over, and they move away and continue on into the solar wind. Here, for a magnetized world, you get something that looks more like Earth if you've seen images of or diagrams of what Earth's magnetic field should look like. But in this study, he didn't look at atmospheric escape. But he did notice that the morphology of the magnetosphere changes, how it looks, and therefore how it should interact with its environment is very different. Some later studies have come along and showed that the escape of charged particles from the atmosphere does change. So I'll show you some of that here. So here are 2 more studies for those of you who can see the slides. For those of you who can't, it's not a big deal. In the first one, this is someone who investigated Earth, and they varied the strength of Earth's magnetic field here on the x-axis, the dipole moment. How strong is the magnetic field? And on the y-axis, they didn't look at atmospheric escape. Their model wasn't capable of examining that. That's pretty hard for Earth. But they could think about how much energy was available to the atmosphere from the solar wind. And that's what's meant by Joule heating power. It's how many charged particles are colliding in the top part of the atmosphere and how much power and energy is associated with that. And they see that for really weak magnetic fields, there's not much energy available. And as you increase the strength of the magnetic field, there's more and more energy available for the atmosphere. But at some point, it either levels off or starts decreasing again. You can actually have too strong a magnetic field for Earth and not heat the atmosphere that effectively. And that's because those strong magnetic fields confine particles. They don't allow them to move nearly as freely. So there's sort of a happy medium, at least in this study, for Earth. Another study that was done by someone who works a lot with MAVEN data, Chuanfei Dong, he studied a Venus-type world, both with and without a magnetic field. And he looked at the morphology of the magnetic field and how it changes and noticed that it was very different, and also noticed that the escape of the atmosphere changed as well as you added a magnetic field. And I'll give you some numbers on that in a little bit, because there are now several different studies that have been done and they disagree. So here's some caveats about thinking about things with computer simulations. And I love interacting with the simulationists, and I've started to do some of that work myself on a small scale. And I think it's an incredibly valuable way to learn about physics and how things interact. But using them like weather models, like meteorology models, comes with some dangers. How do you validate your results? How do you know if you're right? Okay, in a computer simulation, we can turn off Earth's magnetic field, but how do you test that you got the right answer? You can't do that in real life unless you're some kind of evil superhero or something like that. Also, when you do that, do you know if your results are sensitive to other parameters or that you've got the right physics in your model? You're the one who decided what equations to put in there, or there are some equations that were actually important that you decided to neglect. I'm talking about escape of charged particles. And magnetic fields tell charged particles how to move. The solar wind is made up of charged particles, so it's a very sensible thing to think about. But not everything is charged. An escape of charged particles is only one of several loss processes. And most of the modeling that's been done so far is focused on charged particles. Finally, I mentioned this earlier in the slide, strong magnetic fields present major challenges for global simulations like this. I can briefly explain why. The stronger the magnetic field is, the more curvy your particle trajectories become. And the more curvy they become, the smaller the spatial resolution you need for your model, and the smaller the time steps you need for your model. So suddenly, you go to needing a ton of computer resources, a ton of computer memory, a ton of computer time when you add magnetic fields. Okay, so simulating them is hard, and you don't have a great way to figure out if you're right. Okay, so now let's talk briefly and go back to an undergrad level for just a minute. This is something I also use in undergrad classes, so please indulge me. Let's talk about Earth's magnetic field in comparison to Mars. And those of you who have been to multiple of these webinars already probably know about the Mars magnetic field. For those of you who don't, I'll explain it now in just a minute or two. So here's Earth's magnetic field, and you could think of it as a big bar magnet sitting at the center of Earth. And though if you could spread iron filings all around Earth, you'd see those iron filings align themselves in the magnetic field. And the way that they align, the direction of the forces, we refer to as magnetic field lines. So the magnetic field lines at Earth come out from the South Pole, actually, and then re-enter Earth near the North Pole. So that's, if you close your eyes, you can picture what Earth's magnetic field looks like. It's these two Dumbo ears, basically. Now, pretend you're in a spacecraft flying 400 kilometers above the surface of Earth. When you're above the North Pole, all the magnetic field lines that you fly through are pointed down towards the surface. When you fly above the South Pole, all the magnetic field lines that you encounter are pointed up, away from the surface. When you're near the equator, all the magnetic field lines that you encounter are oriented horizontally from south toward north. Okay, that's one thing, the orientation. The next thing is how strong is the magnetic field. And in this diagram, that's depicted by how close together the magnetic field lines are. Near the North and South Pole, the magnetic field is strong. Near the equator, the field lines are more spread out, so the magnetic field is weak. So in a spacecraft that actually measures Earth's magnetic field, you could fly around at 400 kilometers and measure the magnetic field 400 kilometers above the surface, and you could say which way is the magnet pointed and how strong is it. And then you could make a map every surface of what that looks like. And so that's what I spent my PhD thesis doing, at least in part. I'll call that a global compass map. And so for those of you who can see the slides, you see that it's relatively well organized and kind of boring. Every place above Earth that you would visit in your lifetime, the field is oriented from south toward north. And near the equator of Earth, the field is a little bit weaker than near the poles. And if you're adventurous enough to travel into the Canadian Arctic or down to Antarctica or near it, you can see that the orientation of the field there can be pretty different. It can point due east or due west. All the field lines are diverging in the south and converging in the north. And this is all consistent with the diagram that I just showed you. Okay, for those of you who can see the slides, let me show you this same map for Mars. And this is what I did for my PhD thesis, at least in part. Here it is. You don't see anything. My mother is so proud of me. But if you look closely, you can see that these latitude-longitude lines in the slide, the black stripes, they've been crossed every once in a while by a little arrow. So I really did draw Mars' magnetic field on here, but it's incredibly weak compared to Earth's. So our eyes can't make anything out of it using this color bar. So in the next diagram, as I advance one, I'm going to change this color bar. Instead of 50,000 nanotesla, at 400 kilometers. I'm going to change it to something like 250 being the max. When I do that, or 200 being the max, when I do that, when I really zoom in on weak fields, you can see that the Mars field has a ton of structure. There are places where the field diverges. There are places where the field converges. There are places where it points north to south. Other times, south to north and north to south and east to west. There's strong fields and weak fields and parts of Mars where there's no field at all, no measurable field. So let me see what's next. Okay, so our inference here, without actually showing you a map of Mars, is that this magnetic field of Mars is in the crust of the planet, in the outer 40 kilometers or so, and 40 kilometers compared to a radius of 3,400 kilometers. So it's just in the outer part of that onion skin. And even though this is much, much weaker than Earth's big global magnetic field, it's actually 10 or 20 times stronger than any magnetized region of Earth's crust. So these are some of the strongest magnetized rocks that have been measured anywhere in the solar system. The reason they're so strongly magnetized is that Mars used to have a magnetic field like Earth. That's the only sensible explanation, the only explanation that works, and it only barely works for Mars, but nothing else makes sense. And so Mars used to have a global magnetic field. About 4.1 billion years ago, that magnetic field shut off, and only the magnetized regions of the crust remained. Any part of the crust that got heated up after the magnetic field shut off lost the signature of its magnetization. So any place that has no magnetic field here is a place that got heated up after the Mars magnetic field shut off. I intentionally put the color bar here above all of Mars' big volcanoes, the Tharsis region, because that's incredibly unmagnetized on Mars.
So
okay.
A question about the orientation. Can you kind of, you just pointed out Tharsis, could you point out where Hellas Basin is?
Yes, and sorry, for undergrads, I often have a map that I toggle back and forth between. I could pull that up if you want, but for now I'll just show you. So Tharsis is over here. Okay, Valles Marineris is over here someplace. Hellas Basin is down here in the bottom left of the diagram that's unmagnetized. Argyre Basin is over here. And this is a place on Mars that's really heavily cratered, Terra Serenum. It's some of the oldest surface on Mars, and that has the strongest magnetic fields. And most, but not all, of the northern hemisphere of Mars has no or very weak magnetization. The one exception is up here right near the North Pole. There is a weak to moderate region of the crust that's magnetized.
And we have another question. Are these regions with the magnetic rock, are they stronger than, say, rare earth magnets?
Not necessarily, because these are, but they are on, let me try and answer this question in a sensible way. If we were to orbit Earth at 400 kilometers with Earth's magnetic field shut off, the global magnetic field shut off, we would only measure magnetized regions of the crust. And the signatures that we would get from Earth at 400 kilometers above the planet are a factor of 10 to 20 weaker. And that could mean a number of things. Number one, it could mean the magnetization of the rocks themselves are stronger on Mars than on Earth. So there's some really strong magnetic mineral there that is rare on Earth or doesn't get incorporated on Earth. Another option is that the magnetized rocks are more coherently organized on Mars than on Earth. The Earth rocks could be, an individual rock could be just as strongly magnetized on Mars, but they've all been jumbled up and randomly oriented on Earth, while on Mars they're still organized, and they're 1,000 kilometers long by a couple hundred kilometers wide by tens of kilometers deep. So it's probably some combination of the two. Mars is red because there's a lot of iron there on the crust, in the crust that's oxidized. Minerals that contain iron are usually pretty magnetic. So you might expect a lot of magnetite and a maghemite on Mars, maybe even more than on Earth. And those are very easily magnetized and can retain strong magnetic field. But certainly the scale of the coherent magnetization is important on Mars too.
Thank you so much.
Okay. Great. So what does this have to do with habitability and life? For those of you who can see the animation, great. If not, my words should suffice. The magnetization on Mars, while weak compared to Earth's magnetic field, is strong enough that you expect pockets of the atmosphere to be protected and shielded from the solar wind. So there's an animation playing that shows really where Mars' atmosphere should be protected from the solar wind. And there are some places where it shouldn't be protected at all because there's no magnetization. There are other places, especially in the southern hemisphere above that Terra Serenum region, where the atmosphere should be really strongly protected from the solar wind. The solar wind should have a lot of trouble accessing those regions. Who cares? Well, I care in terms of this question because I think that makes Mars a possible Rosetta Stone for answering whether magnetic fields are important. We're not evil superheroes. We can't turn off Earth's magnetic field and measure what happens, at least not on human timescales. And the computer simulations, while really valuable for understanding physics, it's hard to prove whether they get things right or wrong. But Mars has this great, and it's hard to compare, say, Venus and Earth, because they're planets that differ in multiple ways. It's not just that Venus is exactly like Earth except missing a magnetic field. It's exactly like Earth but missing a magnetic field and closer to the sun and other differences as well. So it's hard to perform a control experiment. But Mars has a built-in control experiment. It has regions of the crust that are magnetized and regions of the crust that are not. This allows us to say, all other things being equal, is atmospheric escape more important in the unmagnetized regions of Mars or the magnetized regions of Mars? And all the escape processes that should occur both on Mars and on Earth and on Venus, all the escape processes that occur on both kinds of objects, magnetized and unmagnetized, should be occurring at Mars as well. So I think it's a really great control experiment. So here's where we are. When simulations add crustal magnetic fields to their models, and early on, say 15 years ago, no simulation had crustal magnetic fields in the model. That was too hard for them. But computer simulations and computer resources have become abundant enough that now they can put those complicated magnetic fields in. And when they do that, some simulations show that atmospheric escape rates change by a factor of 30 or more. Other simulations show that atmospheric escape rates change by only 10%, basically a negligible amount within our measurement uncertainties. And so on the slide, for those who can see it, just pay attention to the solid black line. This shows the escape rate from the Mars atmosphere as Mars rotates through a day, from where the strong crustal fields are on the day side or the night side. And you can see that this is a slightly different experiment from what I just talked about. When simulations rotate crustal fields through a day, some models suggest that atmospheric escape should change by 50% or more, factors of 2. Others suggest that it's really kind of a 10 or 15% effect. So different computer simulations give different answers yet again. And that doesn't mean that the computer simulations are bad or that we can't learn anything from them. It just means that we're still trying to understand how the entire system operates. So we also have measurements, for example, from MAVEN that's orbiting Mars. So what do those tell us? One of my jobs on MAVEN is to measure how many charged particles are leaving the atmosphere. And so that's one of the things that I've worked on. And so let me show you where we are on that. One thing that I do with the observations is I draw an imaginary sphere around Mars, and every time the spacecraft passes through that sphere, I add up how many particles are moving away from Mars. And so I paint by number for the Mars atmosphere. How many particles are escaping through this shell on the day side and the night side? And I can create maps of atmospheric escape on Mars, and I can add up those maps to give an escape rate. And I can do that for all of MAVEN's observations, but I can also do it for times when the crustal fields, the strong crustal fields on Mars were on the day side of the planet, and times when they were on the night side of the planet. So I can separate the observations. And when I do that, I find that the atmospheric escape rates from Mars vary by about 30%. So it's not a 10% effect, but it's not a factor of 30 either, a factor of 10. It's somewhere in between as Mars rotates. But there's an asterisk on that statement because we still haven't been, or even though we've been orbiting Mars for 3 years, we're in our third Earth year of making observations, we still haven't covered all of the regions enough times for me to feel really confident about that result. So this diagram on the top of the slide only focus on the right-hand panel. And this basically shows what the atmospheric escape rate is when different parts of Mars are facing the sun. And when some crustal fields are facing the sun, atmospheric escape rates go down. And when the crustal fields move away to the night side of the planet, atmospheric escape rates go up. So this has been called into question by a colleague of mine working with the European spacecraft, Robin Ramstad, and he's was a graduate student as little as a month ago, but I've just hired him as a postdoc, and so we're going to tackle this together. And when he looked at this same question using his spacecraft data, he found that atmospheric escape varied by a factor of 2.5, so it was a big or important effect for his data. And there's a reason to put an asterisk there. His data are organized in a way that you're not sure that the magnetic fields are the only thing causing the difference, because he's measuring some magnetic fields at one time of year and other magnetic fields at a different time of year. So it could just be annual variability. So sorry to get into some of the weeds there, but it might be fun to hear about. At least it's fun for me to talk about. So what we really need to do, I think, is instead of measuring the global escape rate from Mars, like has been shown on this slide, we need to measure the escape happening from different regions specifically when we pass over them. So I now have a graduate student that's just started tackling this. As a matter of fact, I saw his first plot of analysis last Thursday from this kind of analysis. And we're going to do studies of individual regions. And then we're also going to look at the variation and not just charged particle escape, but the other kinds of processes that strip particles from an atmosphere as well, as Mars rotates or from different geographic regions. So that's where we're headed to. What do the colors correspond to on my diagram? Sorry, I left off the color bar. Light blue means the atmospheric escape is not very strong from that region. Dark blue means it is very strong from that region. And this is a color bar that's logarithmically scaled. So differences in shade can account for 7 orders of magnitude from the lightest square to the darkest square, or a factor of about 10 million difference. Okay, so now I'll wrap up, and I know our time is almost done, but I only have a couple points to make. Why should we care about this? For me, the big thing is exoplanets, planets orbiting other stars, and we desperately want to know which of these planets are habitable, which of these planets could be Earth-like, which of these could support life. And you can see when you go and look up popular science news stories that are extracted from published papers, that there's still this idea that Earth-like exoplanets may have magnetic fields capable of protecting life. And in stories like this, they talk about protecting the atmosphere from being lost to space. So we really need to figure out whether that's correct or not. Do magnetic fields protect the atmosphere? Do we need to be looking for other worlds with magnetic fields, or does it not matter? Also, you'll see news stories like this, where brown dwarfs, these objects sort of in between Jupiter, planets, and stars, have started to have magnetic fields detected on them. So people are actively looking. And so that's great, that's really wonderful. But do these types of discoveries tell us anything fundamental about habitability or not? They certainly tell us a lot about the interior of the world and how it's interacting with its environment. So this is my last slide, and it's just a return to these three questions. And I'd like to give you sort of my preliminary guesses on all three questions. So all other things being equal, does a planet with a magnetic field lose less atmosphere than a planet without? I think so far our analysis of Mars, the Rosetta Stone, suggests the answer to that question is yes. If so, is that reduction substantial enough to really matter? I think the jury's still out for Mars, and my guess right now is that it depends upon the size of the world. For a comet that's small, that has a hard time holding on to its atmosphere, having a magnetic field could make all the difference. For Jupiter, that's big and it's easy for it to hold on to its atmosphere, having a magnetic field may not make much difference. So my answer to that question is it depends. Finally, is a magnetic field required for a planet to be habitable? I think if the answer to this middle question was depends, that automatically makes the answer to the last question no. That you don't necessarily have to have a magnetic field to be able to support life at the surface of your world. Okay, so I will stop right there. Thank you for listening, and I know I went right up against the edge of the hour.
Thank you so much, Dave. Someone posted a question to me for you as well earlier, and I think I know the answer, but I wanted to double check with you. He asked whether by mapping the magnetic fields on Mars, are those at all related to future human settlement sites?
Yeah, this is a lovely question. It's a great question. And the sad answer, in my opinion, is no. Mars has a thin atmosphere compared to Earth. It's 0.5% the thickness. But in order for a damaging radiation particle to make it through the Mars atmosphere, it still has to have kind of a lot of energy. And the energy that it has to have to make it all the way to the surface of Mars is so great that the relatively weak magnetic fields on Mars don't make a lot of difference. So the magnetic regions on Mars, even though they shield the atmosphere, they don't actually provide a lot of radiation protection for future astronauts or cosmonauts or humans on the surface of the planet. But where it is important is at higher altitudes, up above the surface. Any particles that are coming screaming into the atmosphere, they get absorbed at higher altitudes, don't have to have nearly as much energy. Those low energy particles get pushed around by the magnetic fields a lot. And so it can make a big difference in the amount of energy being deposited in the atmosphere and the type of chemistry that you might expect in different places, and how the atmosphere might even move in different places. So even though the answer is unexciting for the surface and for human exploration, in my opinion, it's really exciting for the atmosphere itself.
Thank you. Folks, any final last questions for Dave?
There's one here that I see. Do you know of any groups doing simulations that take into account both planetary magnetic field evolution and a changing stellar wind over time? Not yet. So I have a student that's tackling simulations of magnetic fields at different strengths, and she's should have her first set of results in about a month. I know of another colleague that's looked at variable strength magnetic fields and independently looked at variable strength stellar winds. But I don't know of anyone yet who has put together sort of a time history of how this all should work, taking into account both the change in magnetic field and the change in stellar conditions.
Thank you. Folks,
Sure.
If anyone has any other questions, you are also welcome to send them to Tom or to myself, and we can pass them along as well. Thank you so much. So everyone who's joined us, thank you for your time. Dave, thank you so much for your time this evening. This was a great presentation. We enjoy it. Very interesting.
Thank you. And I know one person just asked me a private question, so I'm happy to stay on and sort of answer that out loud, even though this is the official end. But thanks everybody for indulging me and letting me show some of this stuff that really interests me.
I think a couple of us might listen to the answer and the question.
Okay.
Thanks, Dave. Thanks, Christine.
Thank you. So for those of you still around, I got asked about the magnetic pole flip, and I assume that that person is asking about the reversal of the magnetic pole on Earth. And this happens on Earth, and it may have happened on Mars too. There's no reason that it shouldn't have. And it happens in our sun every 22 years. Actually, every 11 years it flips, and then 11 years it flips back again. The same thing is thought to happen at Earth as well. And it's not what I just showed with my hands in the video. It's not that the whole thing just slides around so it's pointing the other way. Instead, what is thought to happen is the magnetic field inside the planet reorganizes itself. It's almost like a yo-yo string getting so tightly wound that it needs to unwind itself and start winding again in a different direction. The net effect for us, or for people who think about the magnetic field at the surface of the planet or above, is that Earth's magnetic field, when this happens, shrinks and gets weaker near the surface. It's got the same amount of energy, but it's just more compact inside the planet. Then it turns over, and then it blossoms back out again. This happens every 100,000 or 200,000 years or so, something like that. So fairly often in the grand scheme of 4.5 billion years. And the flip itself takes a couple centuries, maybe even a millennium to complete. I can't quite remember. So that means that Earth's atmosphere, when this happens, quite likely gets left exposed to the solar wind for up to a century. And Earth behaves or interacts with the solar wind maybe similar to the way that Venus interacts with the solar wind. It's left exposed. So you'll see news stories. I saw one last month. I see them every few years that suggests that this is starting to happen for Earth. And the idea is that before Earth's magnetic field starts to shrink, it kind of starts to wander. And the wander of Earth's magnetic pole has started to speed up over the last couple decades, which could mean that one of these flips is about to happen, and we're about due for this to happen. I don't think that this is an incredible cause for concern for our atmosphere. Number one, this has happened a ton of times, and guess what? We still have an atmosphere. And in part, that's because we still have volcanism that's outgassing new atmosphere all the time. Number two, what we're learning from studies of Mars and Venus is the time scale for stripping of particles is pretty long. It would take 1 billion years or more to lose an Earth's worth of atmosphere. Maybe even 7 billion years, longer than Earth has been around. So leaving Earth's atmosphere exposed for 100 years doesn't mean our atmosphere is all going to blow away. We'll still retain it. Maybe atmospheric escape will go up. The answer to my question for this talk holds the answer to that question. But some cool things could happen. We could end up getting aurora all over Earth with the magnetic field effectively weakened and shut off more or less at the surface. We could get really cool chemistry happening. We could get certain biological systems, certain species that use the magnetic field to function and to navigate are going to have a hard time in that century functioning and might have to develop other ways. So it's still a really cool thing to think about. And it's something that I've been considering submitting a funding proposal to NASA to examine more, because to be honest, there are not very many papers in the literature at all. I know of maybe 3 in the literature that have thought about what will happen to Earth's atmosphere when this happens. So I think it's a cool thing to think about for Earth.
And the questions keep coming, Dave. If you want to respond to them, you may, or if you're running out of time, we can go ahead and we can make sure that we respond further to Carol and to Stephanie as well. Please read my answer to see if my answer was correct or inaccurate as well.
Sure, yeah, I'm happy to respond. So is Mars' lack of a global magnetic field not accelerating the atmospheric loss to space? And I guess it's good that you're confused, because the very inarticulate way that I addressed that question in this talk was to take an hour to say, I don't know. That everybody thought for 30 years the lack of a magnetic field meant Mars was losing more atmosphere. That may not be true. It may be just that Mars is smaller than Earth. And because it's smaller, it has a harder time holding on to its atmosphere. And maybe that's the reason that we think Mars lost a bunch of atmosphere in the past compared to Earth. So I'm trying to figure out the answer to your question. And your alternate question, the question that you asked at the end, does it basically just depend on gravity? If it's true that magnetic fields aren't important, if that group of scientists ends up being correct, then your alternate explanation is what we're left with. The difference is just smaller gravity on Mars. Yeah, and Carol's answer is correct. Stephanie, how does this relate to possible terraforming efforts and sustainability? Yeah, okay, so, and this is something that made a bit of a newsflash maybe a year ago. Jim Green from NASA headquarters wanted to start thinking grand thoughts about what to do at Mars in the next century, what we need to do to be ready for humans to exist on the surface. And so he was thinking of having a big magnetic field put in orbit around Mars. You have some sort of spacecraft that has a really strong magnetic field that can protect the whole planet and keep the atmosphere from being stripped away. And in addition to that, you tow in comets that have lots of water and carbon dioxide in them. You crash them into the planet and you make the atmosphere more thick. And then the third thing you do is you melt or sublime the polar caps on Mars and put all of that ice into the atmosphere as vapor. So this combination of adding atmospheric particles and protecting the atmosphere from being stripped by using a magnetic field was the idea that he proposed. And that may be a great thing to do, that may be worthwhile, but one thing that we're starting to learn from MAVEN is that the time scale for losing the atmosphere is long. If you were to crash a comet into Mars and add a whole bunch of new atmosphere, it might take 100 million years for all those particles to be stripped away to space. And on human time scales, who cares? So you might not need the magnetic field to protect yourself. Instead, you just make sure every 10 million years, throw a new comet into the surface. Sustainability on really, okay, that's for Mars and for things in our stellar system. For planets orbiting other stars, if we really want to get science fiction and go into the future for humanity, the timescales for loss there, especially around certain types of stars, can be much faster. And so then these kinds of ideas important if and when they settle on planets orbiting other stars. Those other stars can be really violent places, and places that make it hard for you to keep an atmosphere that's a happy place for life.
And one more question was posted to me by Rich. He said the term particle leaves ambiguous which chemical species are eroding. He was wondering whether you would expect the loss of some things like hydrogen to be different relative to oxygen, nitrogen, oxidizing agents, and was wondering if that accounts for the predominance of iron oxide and perchlorate salts.
Okay, can you?
Yeah, the term particle leaves ambiguous which chemical species erode. One would expect the loss of reducing species, H, to do, which I think he means to be more which leaves oxidizing agents, oxygen, nitrogen, etc. Does this account for the predominance of iron oxide and perchlorate salts? Is the atmosphere more oxidizing because the hydrogen has eroded away?
Yeah, so we don't know the answer. And that's one question that we want to tackle as MAVEN continues to take data, as we keep having to go back to NASA to ask for funding to keep making observations. The particles that I was talking about in most of this talk were oxygen, either oxygen atoms or oxygen molecules, so O or O2, because when we look at our charged particle observations, that's mostly what's escaping. And a little bit of CO2, carbon dioxide. We have almost no information on how much hydrogen is escaping as charged particles, because it's hard for us to tell hydrogen from the planet apart from hydrogen in the solar wind. However, we can hide escaping as neutral particles by looking at our ultraviolet observations from MAVEN, and that suggests that hydrogen is escaping in really large amounts, not through charged particle interactions that depend upon the solar wind, but instead just because hydrogen is really light and Mars has a hard time holding on to it. But what we don't know is how much hydrogen is escaping relative to oxygen. Our error bars are still too large to tell us whether hydrogen and oxygen are escaping in the ratio of 2 to 1. Therefore, we don't know if we're maintaining that stoichiometric ratio, or if the atmosphere is becoming more reducing or more oxidizing over time. Certainly, you don't have to have the atmosphere be very far away from being balanced to get a lot of oxidizing going on at the surface. So it doesn't necessarily require that you invoke a lot of escape of one species relative to another to make Mars red. You just need oxygen in the atmosphere.
And we've had one more question sent to me, and I'm telling everybody that this is going to be the last one. It's
no problem. But
question,
my last name is Brain, and so it's really easy to find my email address, and you can always email me a question.
Awesome. Thank you, Dave. Hilda wanted to know whether magnetic field changes have a big enough impact to actually affect orbital mechanics.
Whoa. I don't know, but I doubt it. The magnetic field, deflects the solar wind particles, and it can really change their momentum, which means that momentum is added to the planet. And if you add momentum to the planet, that is going to change the orbit of the planet. But it's really, when you compare the magnitude of those effects, it's so small. I mean, I would imagine it's something like factor of 10 to the 28 difference, how much momentum is being absorbed by the solar wind compared to how much momentum Mars actually has. So that momentum change is really important for individual atmospheric particles, but for a planet itself that's 10 to the 26 kilograms, I imagine that it is negligible, even on 4.5 billion timescales. I imagine you would need, I don't know, 1,000 billion years or something like that to have it be important. I know 1,000 billion isn't a real number, but that's what I said.
Awesome. Thank you again so much. Rich wanted... Go ahead.
No, I think someone may be unmuted and you got an echo.
Okay. Tom, did you have any last words to say?
No, other than thanks, Dave. We appreciate you doing this, and I think your mother would be proud because you're doing science with a capital S and a small s and all sizes in between. So, thanks.
Okay. Thanks, everybody.
Thank you so much. Everyone really appreciates this, Dave. We thank you for all your time.